Hey guys, thank you for making it out here. Thank you for braving it through all the smoke and fires, and it's good. LA is burning once again. So we have two really good speakers tonight. We got Brandon Phillips and Jamie Isaacs. Also, huge thanks to Patient Pop for hosting us and the pizza and the just the space in general. This is like a really nice setup. Thank you for clapping. Just to throw a plug out there, they are hiring, so if you're interested. I have to say that because they're hosting. One last thing before we get started. I've started doing this thing where I print golden gophers for our speakers. So I have one for Mr. Phillips over here.
Thank you.
Yeah. Then one for Mr. Isaacs. It's got their name written on the back and everything.
Oh, thank you.
Yeah. So those are fun. Little prize and incentive for you to speak if you'd like. I might do some backtracking for past speakers, Kamesh, Marion. So we'll go ahead and get started with Mr. Isaacs on event modeling.
Right on. All right. Thank you. My name is Jamie Isaacs, and code has been my craft for over 20 years now. And I've recently learned something from the domain-driven design community called event modeling, and I'd like to cover that with you today. And what we'll do is we'll show you how to model your domain with Post-it notes or sticky notes and turn that into actual code. I prefer to write tests first, so I'll show you what that actually looks like as well. So this talk is broken up into 3 parts. We'll cover what event storming is, how to do that with a simple example. The CQRS architecture on how you might put that together with event sourcing. And then we'll cover some code samples, again, test first. So what is event storming? This is a workshop method for looking at your domain and making sense of it on a whiteboard with your team. Now everyone will do this. It's just like a brainstorming session. You'll write events on Post-it notes and put it on the board. And those Post-it notes come in 3 forms in this example. You'll have events, commands, and then constraints. Now, events are historical facts. Those things happen in the past. You can't change those. A command is an imperative action. This is the thing that you want your system to do. This is the entry point into your application. And then a constraint would be a policy or a rule applied to those previous events. And let's jump into what an event is. So I'm going to do a bank account example. And for the first event I can think of is an account was opened. Again, this is in past tense. This is something that has happened. I cannot change that fact. Money was deposited is another event. Money was withdrawn. Maybe an account was opened. So these 4 events are the primary events in the system we're going to cover. Next, how might those get emitted? Well, they might happen with commands. So for an account to be open, obviously, let's open an account. That might be an API endpoint, open the account. For depositing money, again, just deposit money. Same for withdraw money. To close an account, you close an account. Pretty basic. Now, a constraint, we want to look at how we might emit events. For the example of opening an account, in this contrived example, we're just going to always emit that event. If someone attempts to open an account, we're going to emit this event. Now, you might, for your example, you may want to look at a background check for a customer before you open an account with them. But to show you what this would look like in code, we're going to keep it simple. For depositing money, we need to determine whether an account is open. Okay, we can't just accept your money. We need to apply it to an account ID. And if we don't have one, an event will be raised called deposit failed. To withdraw money, it's a little more important, a little more interesting to look at more events to determine whether funds are available. And if not, the withdrawal will be denied. To close an account, we don't want to close an account with a balance, so we'll check, does an account have a balance? And if it does, we'll fail to close the account with the balance. So this is a way to look at the dependencies and how to write your code. For the always constraint, there are no real dependencies because you just need the command. To determine whether an account is opened, we need to look in the past to see, was there ever an event in our system called account was opened, and potentially whether an account was closed. To determine whether funds are available, we need to look back to see, was there money deposited or was money withdrawn. To close an account, we need to look at a lot of things, whether an account was opened, whether it was deposits or withdrawals, etc. So this is the system we're going to cover for the rest of these slides. And I want to call out one more thing. You might have heard of an aggregate, and it's a way to organize the events around a centralized thing. And we'll get into that in a few slides. So now I want to talk about how you might design an architecture around this system. And CQRS is one way in which you can do that. You can also add event sourcing on top. And what that means is, well, CQRS is a command query responsibility segregation. And if you've ever heard of CQS, which, by Bertrand Meyer, it's a way to separate the responsibilities between commands and queries. Commands can change state, but queries can only return values. CQRS takes that to another stage, separating into a read model and a write model. So what would that look like for real? You have an API that might have commands. On the other side, you might have queries. Now the commands go into the write model. Some business rules are applied. Events could be emitted, which go to an append-only event store. Now you can never change these events. They're always going to be a pristine point in time of what happened at that point in time. Those events go into an event bus, which get subscribed to by a projection in the read model, and that's what supplies queries with their information. Another thing that could be subscribed to the event bus is what are called process managers. And process managers can emit more events or trigger other commands. Now it's important to note that process managers cannot communicate with the read model because the read model is eventually consistent. We need to go look in the write model. And the way to do that would be to use an aggregate. Now an aggregate can read and write from the event store. And that's the basic CQRS architecture. Let's look at some code examples, but first we'll go into a sequence diagram for how a command might be handled. So you might call the execute method on a command handler with the command. That's what that little green envelope is. You go to the event store, give me all the events for the aggregate. You go to the aggregate and say, create yourself with these events. And then we call handle on the aggregate. And the aggregate will potentially emit events in which we save to the event store. All right, so let's just look at the real code. Enough. So I like to do tests first. And for the first example, we'll look at what happens whenever you want to open an account. Now, there's no business rules to apply here, so it's a good first step to see how you might do this. We want to test the open account command that it emits account was opened. So given we have an application, when we execute the open account command, then we expect these events to be emitted, which is account was opened. That's all you have to write in the test. Now let's implement that. So the app has an execute method. It takes a command. We switch on the type. We determine it's an open account command. Now we defer to the aggregate to handle this command. That code is here. Let's see. We go to the event store, get all of the events for the aggregate, which in this case is the account ID. We create the aggregate and then call handle on the aggregate. That handle method takes the command, switches on the type, determines that was an open account command, and we're just going to emit account was opened. And that's all. There's no other things you need to write. And then we persist those events that are emitted from the aggregate to the event store. Okay, let's look at a real more interesting example, because that didn't have anything other than just always emitting an event. Let's test withdrawing money. So when funds are available in the account, we're going to emit money was withdrawn. Okay, so given we have an application, and also that we have these events existing in the system, account was opened, money was deposited with 100 units. When we execute the command withdraw money, then we expect money was withdrawn, and the new balance is 25 units. Okay, let's look at that execute method. We take in a command, we switch on the type, we see that it's a withdraw money command. We go handle with the account aggregate, go get all of the events for this aggregate, and then call the constructor on the aggregate. That's a common Go idiom to create a method called new for the object, which is the constructor. And in this example, it takes the events. We create the object, and we iterate over the events, calling the transition method. Now that transition method takes a single event. We switch on the type. We determine this was money was deposited. So we go into the state of the aggregate and increment the balance by the amount. If we got a withdraw, we decrement the balance. And then we return the aggregate and then call handle on the command, on the aggregate. It takes that withdraw money command. Now we get to write some real code. If the state on the aggregate, if the balance on the state has the funds available, or if it does not have the funds available in this example, we'll say withdrawal denied and then have a gated return. Otherwise, we'll emit an event, money was withdrawn, and then say the new balance is the current state minus the new balance, or minus the amount that was requested to withdraw. And then we save those events to the system. So that's it. That's all the code you have to write. There's one if statement, a few events you need to know about, and there's no repositories that you have to mock out. There's no service layers that you have to mock out. It speaks the language of the domain, right? Normally, when you design a system, the language of the domain changes, that it diverges from the code. The code tends to go into technical details and have technical topics and technical language, but your domain always stays the same ubiquitous language and changes for different reasons than what your code architecture might change. When you design a system this way, with event modeling at the core, with event sourcing as the core, the code can change with the domain as it changes. So now let's look at what a read model how you would code a read model. In this example, it's called a projection. And we're going to, for the most simple example I could think of, just count the number of events in the system. And we're going to assert that it does count them. So given we have this projection called count events, and we have an in-memory event bus, we're going to subscribe to that bus. When we publish these events into that bus, account was open, etc., there's 5 of them, then we expect the total to be 5. Okay, let's look at the code. So we create the projection. We create a field called total events to keep track of the state. This projection implements the subscriber interface, which has an accept method that takes an event and just increments the total event count. Pretty simple. That's all you have to write to keep track of that. Now we want to write something a little more interesting. Let's look at how to total the account funds for all the accounts and potentially for the entire bank. Okay, so given we have this projection, when these events are in the system, an account A was open, money was deposited, withdrawn, account B was open, money was deposited, then we expect the total balance across all accounts to be 75 units and for A and B to have their respective balances. Okay, how would we implement that? Again, we have an account funds projection with a couple of fields to hold the state. We accept the event. If we got a money was deposited event, we increment the total funds, and then we increment each account balance. Same thing for withdrawal, we just decrement. And that's all there really is to it. There's not a whole lot of code you have to write. I think this type of system lends itself well to domains that are complex that aren't simple, right? Like if you have a CRUD-based system, this probably won't work. But if you have a system that changes in ways that you don't expect or that are more complex than you can currently handle, then domain-driven design and event sourcing and CQRS might be the solution for you. So I'm happy to answer any questions you have. Yes? You have the mic?
Kind of externalize your business logic, basically in your business rules. Do you ever see it being used for more technical work, such as getting a schema to remain consistent or something like that? It seems like it's really good for business rules, but do you use it for technical consistency much?
Sure. If you've used Git, like that follows this model. Git is a bunch of events applied on top of each other. Your bank account is literally implemented this way. Does that get close to your question? Well, this is a way you can always build state from this model. If you store all of the events in the system, you can always get to the state. But if you build a system with just state, you can never go back to the past and get that eventual consistency of that state at that point in time. So say, for example, you start off with an event source system, and a year later you have this new idea for a report. Okay? You write that logic, and now you can go back in time to March 1st and play that report back. Right? You couldn't do that with a stateful system. It would be very difficult, if not impossible. because you're not storing those transitions unless you have an audit table, and then you have an audit log, and then you have all these things that have nothing to do with the business. They have everything to do with technical details. So I wouldn't do this for every system, certainly not, but for things that lend themselves well to projections. So if you've ever used Elasticsearch, that's a projection, right? It may not be based off of events, but it's based off of your state. Does that help? Okay. Question here?
I guess what's the state of the art of using a database or something to store the events, and then listening and looking at the code? Is it that you replay every event every time that you need to make a calculation?
Yes. Yes. So you can use things like Postgres to store the data. You can store it as JSON, the payload just to be JSON. To answer your question about how can you efficiently do that, if you're building a projection that has to play back all the events, well, it has to play back all the events. There's just no way of getting around that. If it takes you a weekend to do that, then that's just the cost. There are ways you can save the state. So your projection can persist its current state and then play back from that onward. That's one way to get around that issue. For your aggregates, you store the events by aggregate ID, so it only needs to, if there's 1 million events in the system, it only needs the 100 events that are on its aggregate, and you can efficiently get those out of the system. I've seen event stores in S3, so you just store it as a bunch of files in folders. There's plenty of them out there.
I guess as a follow-up, is the term, like using the term bus, is that normal in this sort of system if you're often relying upon a stateful database versus an event bus?
Well, you can have a stateful system that has a bus as well. Those are called domain events. That's kind of the mediator pattern if you're going to use the design principles that way. They can coexist. The bus is just a way to communicate. It's a mechanism for one bounded context to have its own subscription system, but then also other bounded contexts, other microservices need to subscribe to certain types of message buses. And I didn't call out any one specific type of messaging system or messaging bus because I think they're mostly interchangeable. There are some that you can put a message on the bus to not go in for 3 hours, for example. So you can avoid cron-based systems. Does that answer your question?
Yeah, thank you.
Any more questions? Yeah.
I was mostly just wondering if you had a preferred event store for Golang that you've used that you found to be most effective in your experience, particularly with Golang.
I prefer columnar stores. So I for a local projection or a local bounded context, I might use something like LevelDB because that can run inside of Go. There's an implementation. LevelDB is a system designed by some Google fellows. I believe it was in C or C++. But it's been ported to Go, or at least some parts of it have been. And you could use that. That's what I prefer for really simple localized ones. But if you have a system, you need an event store for a lot of services, I might not use that. I might use something else. I've seen people use S3, which kind of sounds kind of crazy, but it works, and it's so I can't just pick one because it depends.